everyone, and welcome back to another ALLVAR University video. In this video, we'll be talking about athermalizing lenses with ALLVAR Alloy 30. Here you have some aluminum, you have ALLVAR, and some more aluminum and a sensor. And you want to make sure that the lens is going to focus light on that sensor regardless of temperature. And you can athermalize the system by tuning the housing's coefficient of thermal expansion by playing with the length of ALLVAR relative to aluminum. But before you get to something like this, you can use some of our newly available lens tubes. So this is an SM1 tube, and it mates perfectly with normal, commercially off-the-shelf aluminum SM1 lens tubes. So you can breadboard with our ALLVAR Alloy 30 and create an athermal system that you can test in the lab. So to get started, we can use an off-the-shelf lens that is already well understood and well characterized so that we can athermalize the housing to match what the lens does. In this example, we're going to be talking about a doublet, but you can do this with much more complex systems. So if you have a doublet that has two lens elements, element 1 and element 2. You guys already know this. The index of refraction will change with temperature, and the radius of curvature is going to change with temperature due to thermal expansion. So these two contributions to the change in focus, which be here in this case, will push this lens out of focus if the housing doesn't match the change in focal length. So if you have a focal length from here to here, that's the focal length of the doublet, and the temperature changes, you're going to get a change in the focal length of the doublet due to a change in temperature. So all we have to do is match this change in focal length with the same change in length of the housing. So if, for example, you have element 3 right here, this is housing 3, and element 4 for the housing, you can choose two different materials for SM1 lens tubes, for example, or for an assembly. And if this is the length of element 3 and this is the length of element 4 will also change due to a change in temperature, and element 3 will also change in length due to a change in temperature. And we can actually reference this as the total length of the housing, which is equal to the focal length. And we'll also notice that the length of the housing is going to change also. And we can kind of combine these. We know that there's some relationships here. The length of the housing is equal to the focal length of the doublet, and it's also equal to L3 plus L4. We also have a relationship between the change in length of the housing is equal to the change in length of element 3 plus the change in length of element 4. So how do we athermalize? Well, it's quite simple. You really just want the change in length of the housing to be the same as the change in the focal length of that doublet. So to solve this, we can break it up into the mechanical portion and the optic portion. If we look at the optic portion, there's a term called the thermo-optic coefficient, beta. And this is defined as 1 over the focal length times the instantaneous, or the first derivative of focal length with temperature. And this is approximately equal to 1 over the focal length times delta F over delta T. This is a linear assumption that says, for small differences in temperature or for linear changes in the focal length with temperature, you will observe, or you can calculate, the thermo-optic coefficient. On the mechanical side, you have thermal expansion. And thermal expansion is defined as the first derivative of strain with temperature. Now this equals 1 over the original length times the first derivative of length with temperature. Notice that this is very, very similar. The thermo-optic coefficient and the thermal expansion coefficient have very similar forms, the same form actually. And this is approximately equal to 1 over L delta L over delta T. Again, this being the linear assumption. So we can rearrange these to kind of make it a little easier to work with and be able to plug into this equation. So for thermal expansion, the change in length is equal to the thermal expansion coefficient times the original length times delta T of the lens tube. The thermo-optic coefficient, delta F, or the change in focal length, is equal to the thermo-optic coefficient times the focal length times delta T. So now we can plug in the two elements here. So in this case, if we look at the thermal expansion coefficient and the length of the housing, here we have the thermal expansion coefficient of the housing times the length of the housing times delta T is equal to the thermo-optic coefficient of the doublet times the focal length of the doublet times delta T. Now delta T will cancel because it's on both sides. And remember that the focal length and the lens housing are the same length, at least when everything's in focus, and so at the reference temperature. So we can eliminate these two as well. And so as long as the thermal expansion coefficient of the housing matches the thermo-optic coefficient of the doublet, the system will stay in focus regardless of the temperature. Now, I told you that we have an off-the-shelf optic, or an off-the-shelf lens, and we want to athermalize it. And we can do that by choosing the length of L3 relative to L4 to tune the thermal expansion coefficient of this air gap right here. Now, to do that, we need to get this, the housing delta L, in terms of the change in length of element 4 and of element 3. And so to do that, we take this equation and this relationship right here. The change in length of the housing is equal to the change in length of element 3 plus the change in length of element 4. We can expand these using this thermal expansion relationship. And so the thermal expansion coefficient of the housing times the length of the housing times delta T is equal to the thermal expansion coefficient of element 3 times the length of element 3 times delta T plus the thermal expansion coefficient of element 4 times L4 times delta T. Just like in this equation, the changes in temperatures cancel, and we're left with a relationship between the thermal expansion coefficients, the lengths, and the relative lengths of the two elements 3 and 4. We can rearrange this so that we get this equation in terms of the thermal expansion coefficient of the housing alone. So the thermal expansion coefficient of the housing is equal to the thermal expansion coefficient of element 3 times L3 over LH plus the thermal expansion coefficient of element 4 times L4 over LH. Now this isn't exactly useful for us because we want to be able to eliminate either L3 or L4 and get this term in the expression of only one of them, because we know that there's a relationship between LH, L3, and L4. To do that, we rearrange this, and we can say L3 is equal to LH minus L4. And we plug that in to this equation. Alpha H is equal to thermal expansion coefficient of element 3 times LH minus L4 divided by LH plus the thermal expansion coefficient of element 4 times L4 over LH. We can expand this and distribute the thermal expansion coefficient, and what we have is the housing thermal expansion is equal to the thermal expansion coefficient of element 3 minus the thermal expansion coefficient of element 3 times L4 over LH plus the thermal expansion coefficient of element 4 times L4 over LH. Now we can take this and plug it in to this half of the equation. So in this case, beta D, or the thermo-optic coefficient of the doublet, is equal to everything on this side of the equation. L4 over LH times alpha 4, L4 over LH minus alpha 3, and then alpha 3. So now we can take this equation and we can rearrange it, because what we really want to know is how long does element 4 need to be to athermalize this system if element 4 and element 3 have different thermal expansion coefficients. So this is known. The length of the housing is known. The thermal expansion coefficients of the elements are known, elements 3 and 4, and so we're solving for the length of element 4. So in this equation, we can bring together the LH over L4. So we have thermal expansion of element 3 minus L4 over LH. Let's make sure that that's negative. We'll do that. And times the thermal expansion coefficient of element 4 minus the thermal expansion coefficient of element 3 is equal to the thermo-optic coefficient of the doublet. Then we can rearrange this. We want to get everything in terms of element 4, or the length of element 4 is equal to the thermo-optic coefficient of the doublet minus the thermal expansion coefficient of element 3 divided by the thermal expansion coefficient of element 4 minus the thermal expansion coefficient of element 3 times the length of the housing. And remember, the length of the housing is equal to the focal length of the doublet, so that can be substituted directly. Now, the beauty of this equation is this thermo-optic coefficient doesn't necessarily need to be the thermo-optic coefficient of a doublet. It can be the thermo-optic coefficient of any complex lens system. And if you have a single air gap that you're trying to athermalize, for example, between a lens and a sensor, you can use this equation to determine what the length of, let's say, the ALLVAR piece relative to an aluminum piece should be. So you can get the thermo-optic coefficient from a software program and plug it into this equation, and you'll get a very good approximation for how to athermalize this system.